Today's speaker is Kenza Kazi. Kenza is a third-year PhD student in the AI program, and her PhD is focused on applying Gaussian process-based methods to understand precipitation and high-fidelity. Also, the topic which we're going to talk about today. He's interested in climate policy, bridging the gap between science and decision making. And before coming to Cambridge, he integrated masters in physics from Imperial College London. And yeah, looking forward to the talk. Thank you very much.
Thank you, Kesha. Good afternoon, everyone. Yes, as Kesha said, I'm in the third year of the AI for ERTDT, and I'm supervised by Richard Turner at the Department of Engineering and Scott Hosking and Andrew Wall at the British National Facility. Today, I'd like to talk to you about how we can use probabilistic machine learning to improve precipitation estimates in high mountain Asia. So first, I'll discuss why high mountain Asia is so important and why modeling precipitation in this area is so challenging. Then we'll learn about why probabilistic machine learning is an attractive solution to overcome these challenges and introduce a model I'm using. We'll then take a look at the performance of the model with a couple of validation experiments before looking at the results of the model when applied to the whole study area. Finally, we'll discuss the limitations of this project and some ideas for future work. So high mountain Asia is the high altitude area of the Asian continent that includes the Hindu Kush Mountains over here, the Himalayas, and the Tibetan Plateau. Most of Asia's great rivers, such as the Indus, the Ganges, and the Mekong River, originate from these mountains. Together, they work as a water tower, storing snow and ice in the winter, which melts in the spring and summer. So through this mechanism, high mountain Asia supports the livelihoods of over 1.9 billion people by providing fresh water for domestic use, agriculture, industry, and energy through hydropower plants. However, this region is also one of the most sensitive to climate change. As temperatures rise, river flow is shifting from being principally driven by snow and glacier melt to exclusively rainfall. And these changes are expected to lead to more extreme variations in the river flow rate, and in turn, more floods, landslides, and droughts. So these changes, coupled with an increasing demand for water, mean that future water availability in this area is uncertain. And our largest source of uncertainty to this understanding for both current and future water security is precipitation. It may be hard to picture what I mean when I talk about water security risk, but as you know, climate change is already here and happening now, and we can look at events in the recent past to give us a flavor of what is to come. So one such event were the flood in Pakistan last summer. The country received an unprecedented amount of rain, which led to one of the worst environmental crises we've seen. So according to the UN, over 33 million people were displaced by the flooding. So imagine half the UK population having to leave their homes. More than 1,700 lives were lost, and 2.2 million houses were damaged or destroyed. So the floods also damaged most of the water systems in the affected areas, which meant that over 5 million people had to rely solely on contaminated or polluted water from ponds and wells. It's also important to remember that in this climate crisis and in future climate-related crises, not everyone is going to be affected equally. So children suffer more than adults, women more than men, and the poorest communities are going to bear the biggest burden of these disasters. So despite these very real risks, precipitation in high mountain Asia is still very poorly understood. And this can be explained for 3 reasons. The first challenge is the complex topography that makes distribution of precipitation highly heterogeneous with large variability over very small areas. The second challenge is that there are very little direct measurements of precipitation, especially in altitudes above 2,000 meters. We have indirect measurements through satellite observations, but their coarse resolution means that we're unable to capture distribution differences between mountain valleys and ridges. They also struggle to capture extreme events because of the way that these measurements are taken through low Earth orbit satellites, and they also struggle to identify precipitation over glaciers. And the third challenge is that climate models have many limitations in this area. So not only are they computationally expensive to run, as with any climate model, but They're often inaccurate in high mountain Asia because they're not parameterized for the dominant physical processes that take place in mountains, but for those that happen in plains. My PhD research focus around one question: how can we improve these estimates for scientists and policymakers? In order to do this, the predictions first need to be accurate. We should be able to make these predictions from a small amount of data that suffers from missing values. We should be able to make predictions using both gridded and non-gridded information, such as point measurements from weather stations. And we would like to make predictions at new arbitrary locations, not necessarily where the model has been trained before. And finally, and most importantly, the prediction should also have an uncertainty, by which I mean each prediction should have a probability of how likely any given precipitation value is. And this will help us understand the likelihood of extreme events such as droughts or floods. We can achieve all of these 5 conditions using a probabilistic machine learning method called multi-fidelity Gaussian processes. So how do they work? Let's start with probabilistic machine learning as a concept. So rather than outputting a single value like the one we have here, with a probabilistic machine learning method, we'll be outputting a probability distribution. So for each value of y, there is an associated probability. A common probabilistic machine learning method is called a Gaussian process. Well, sorry, a common probabilistic machine learning method is a Gaussian process. So let's first consider this regression problem where we have a set of observations, xi and yi, and these observations are generated by a function f and modulated by a noise term epsilon I. And we're going to assume that this noise term is normally distributed with a mean of 0 and a standard deviation sigma. The function f can be modeled with a Gaussian process. A Gaussian process is a stochastic process where any finite collection of its random variables, so the y's, are going to be distributed according to a multivariate normal distribution. And just like a multivariate normal distribution, a Gaussian process is defined by a mean function and, mu here, and a kernel function or covariance function k. So here the x's represent the input vectors you want to predict that. X prime is another input on another arbitrary input location, and the thetas here represent the hyperparameters of the mean function and the covariance function. So these parameters can be set manually, or they can be optimized through maximum likelihood estimation. Because we are working with probabilities, we can fit the model through the data by using Bayes' theorem. We start by setting a distribution of what we would think the output should look like, which we're going to call the prior distribution or prior. We then update the model with the data, so specifically the probability of the data happening, and then the probability of the model being correct given that data. We then get an updated distribution from that, which we're going to call our posterior distribution. So Gaussian processes are usually represented in plots like this one. Here we can see we have some observations in the form of these blue dots. And from these observations, the Gaussian process is going to generate the posterior distribution. And the posterior distribution here is represented by its 95% confidence interval, which is shown in the shaded blue region. And what we can see is that the posterior is very small and constrained near the observations and gets larger as you move away. The black line represents the mean of the posterior distribution, and we can also generate samples by connecting possible outputs for each of the x's. These are the dashed lines. So Gaussian processes have many advantages as machine learning models. As we've just seen, they provide well-calibrated uncertainty estimates. So assuming that the model is well specified, a Gaussian process knows when it doesn't know, right? It increases the uncertainty away from the training distribution as we've just seen. And these uncertainties, as I previously mentioned, they're very useful in determining the likelihood of extreme events and improving decision-making. They're also really useful for doing machine learning with highly correlated data sets. In many applications, such as these visual ones, observations are not going to be independently or identically distributed, but closely related to one another. Gaussian processes also provide more interpretable machine learning. The GP covariance function and mean function hyperparameters specify explainable high-level properties of the functions that we're generating. And this is very different from neural network weights, where there's no obvious physical correspondence to any of them, at least not directly, just by looking at the weights of the model without any further analysis. And then we also are going to get data efficient machine learning. Because the GP is non-parametric and Bayesian, we can both have model expressivity whilst avoiding overfitting on a small data set or small number of data points.
There's a clarification over here. At point x equals 4,
Yeah,
you don't actually have an observation, right?
point x equals 4, no, it's no observation.
Okay, so when we were in the previous notation, we had x as a vector. That is a vector of observations. Are these partial observations or full observations? In the previous slide, y equals x. So is xi, is that the partial observation with dimension n?
No, it would be the full observation.
I
And
see.
you assume that you have, I guess, like a complete vector,
Okay.
like at those points.
Okay,
What I meant by missing data is more that, you might have very few number of data points with a few number of input dimensions.
okay,
Um,
Each of those is complete.
each of those is complete.
okay.
Yeah.
So in some sense, you have what you want is a full data set, but what you actually have is a partial data set, and that partial data set is x over there.
Yes, so for example, we may have a number of weather stations,
Right.
and they might not be, or like have missing data, like they don't have the measurements of certain given times. And those observations will be heterogeneously distributed in space, not evenly on a grid. So that's what I mean by sparse and.
No, I understand. So when you say x over here, so here x is all the data that you actually have, right? In this slide.
Yes.
And in the next slide, x equals 4, you don't have it. So it's just confusing that you use x in 2 different ways.
Yes.
Okay, good. So as long as they agree in 2 different ways. Okay,
Oh, sorry, I've gone too far.
that's okay.
Yes. Okay. I will look into that more. But the last point I wanted to make was that GP regression and classification is pretty unlikely to fail. And so these GP models can be used pretty reliably as a smaller part of a bigger machine learning system. So examples include probabilistic numerics or reinforcement learning. And then you also have things like automated statisticians, which I can talk about more. But in the interest of time, let's move on to the model that we're actually interested in, which are the multi-fidelity Gaussian processes. So in this case, I'd like to combine Gaussian processes together as building blocks to create a model that can combine data sets of different fidelities. The fidelity of a data set can be defined as a combination of the data's precision and accuracy. So the most accurate set of observations with the highest resolution are referred to as the high fidelity data. And the less accurate and coarse observations or simulation data are denoted as low fidelity data. In many cases, in the real world, high fidelity data can be expensive to produce or to measure, whereas low fidelity observations are usually more accessible and therefore more numerous. A multi-fidelity model then combines low fidelity data sets with the more accurate but limited observations in order to predict the high fidelity output more effectively. So we can define a problem again with the fidelity levels. We consider S fidelity levels producing outputs YTI allocations XTI, where T is any value between 1 and S. And so in this case, YS would denote the output of the most accurate and expensive function to evaluate, whereas Y1 is the output of the cheapest and least accurate function. And the observations at level YT can again be generated by a function FT, representing a multi-fidelity Gaussian process. So ft is basically the sum of two terms, a function ft minus 1, which was fit on the data at the previous fidelity level, and a function f error, which models the bias between the two fidelity levels. Both ft and f error are also Gaussian processes, and because of the additive properties of Gaussian processes and in general normal distributions, the sum of two Gaussian processes is also a Gaussian process. So this equation can actually be solved analytically and be jointly optimized, and we'll discuss why that in different data. And finally, rho t represents the scaling factor and the scalar value in this case. So this particular recursive form of Gaussian processes was first presented by Le Gratier and Garnier in 2014, and I have a reference for the paper at the end if you'd like me to show.
But you don't know about the scaling factors of the bias?
No.
Theoretically, that's not the case. Would that affect the additive property of the Gaussian process if you don't apply to both? So, like, how do you decide the scaling?
So the scaling function is basically based off the covariance and variance of the inputs, basically.
Oh, I see. So it's independent of the bias.
Yes.
Right.
Yeah. Yeah, so we can look at this more visually. I think this makes more sense actually. So in step 0 here, we have our data. In gray, we have our low fidelity data points that are generated by the function shown in the gray dashed line. And these are evenly spaced out. And then in blue, we have our high fidelity data. This is generated by the underlying blue function or dash blue function. And we're going to consider this to be the true function that we're trying to estimate. And we can see that for the high fidelity observations, there are less of them, only 10 points, and the resolution is smaller. So the distance between the points is smaller, or can be smaller. So in our first step 1, we want to fit a Gaussian process to the low fidelity data set, and we're going to call this F1. And this gives us nice uncertainty estimates, just as the ones we saw in the previous slides. With larger uncertainties further away from the training data. In step 2, we then sample F1 at the locations where we have the high fidelity data. And we're not only taking the mean of F1, but also the variance / standard deviation. And finally, we use these values in our observations from the high fidelity data to fit our second Gaussian process. And this gives us a very satisfying fit. We recover the truth function almost perfectly. This is of course just a simple toy problem. In real life, it's a little more complicated than this. Can you not see?
No, there's one thing that's come up with this. I'll just bring it. It's smart too much.
Oh, it's gone.
It's gone. Oh, it's gone. These smart TVs aren't so smart.
So let's come back to our mountains. And we're going to look at a case study for the Bias and Safaj River Basin, which are two major tributaries of the Indus River. So geographically, this is at the borders between Pakistan and India. Here we have a network of 58 rain and snow gauges, which have been active for at least 5 years between 1980 and 2013. And we would like to use multi-fidelity Gaussian processes to combine some model data with that of the gauges. We want to learn the mapping between the inaccurate but complete model data and that of the sparse but accurate gauge data in order to make predictions in this area here where we have no measurements. Great. This is a hard problem. We're trying to make out of distribution predictions with respect to location, but also with respect to elevation, because as you can see, most of the stations are located in here, a low altitude area, and we want to predict here in a high altitude one as well.
That's incredible. You have like nothing in the high altitude area.
No. So before we go off and make predictions, we need to understand how well our method might work. And to do this, we set up some validation experiments where we study monthly precipitation between 2000 and 2005. So I'm going to explain two of the validation experiments here. So we're first going to apply our model to Europe, which is a well-studied area, before we start looking at our case study area. In both cases, we're going to use a multi-fidelity Gaussian process with two fidelity levels. Our low fidelity data set in both cases is going to be era 5 climate reanalysis precipitation data. Climate reanalysis, I'm sure you know, is a numerical weather model that's been run in the past and constrained with historical observations of the climate. And this data is complete and gives us a very accurate picture of what the weather looked like on a day-to-day or month-to-month basis. And it's also gridded on a grid of 0.25 degrees, which is equivalent to 31 by 31 kilometers. So for the high fidelity data in Europe, we're going to be using the value 86 dataset, which unsurprisingly contains 86 weather stations. And these weather stations have been specifically chosen because they represent different climates that are found across the European continent. Then for the BS and subject basins, we're going to be using the gauges I showed in the previous slide. Yes. So we want to know what the model does when we ask it to make a prediction that is at a new location and that is far away from our training set. So what we're going to do is use k-fold plus validation to evaluate the models. And this means we split up the station into groups and train the model on all of the groups except one, and then see how well the model performs on the excluded data. And this process is repeated for each of the permutations of the groups. So here the plots show our cross-validation scheme with our different groups of faults for both of the validation experiments. And as inputs here, we're using time, latitude, longitude, and elevation. Something interesting to point out is that all these experiments are complete in time. We don't have any missing data for the validation experiments, but that also predicting reflected time is actually a lot easier as a problem because the mapping is going to be more stationary with respect to time at the same location than it is when we are changing across space, basically. Yes, so let's move on to the results. A good way of evaluating a model is through a metric called coefficient of determination, or R squared. Just to remind you that this represents the amount of variance in the data that's being explained by the model. So 1 is being a complete match, all the variance being explained by the model. 0 is the equivalent of drawing a straight line through the mean of the data, and any negative values are worse than that, worse than drawing a line. So we can plot the R squared score of the era 5 data fit with a simple Gaussian process as a function, or rather, this is the other way around. We can plot the R squared of the multi-fidelity Gaussian process, multi-fidelity Gaussian output as a function of the R squared of the era 5 data fit with a simple GP. And what we can see is that over Europe, at least, that in most cases we have an improvement over era 5. i.e., data points are lying above the dashed line. And obviously there are some locations where this is not the case, the green dots especially, and that actually represents the cluster that was over the Pyrenees and actually contains both a coastal and mountainous climate. So that might be the reason that the model is struggling to do well on those particular locations. For the upper DS and Salish basins, the results are a little bit more mixed, but we're still getting an overall improvement over era 5. And something that's quite interesting is that we are saving some pretty bad cases, these red dots in particular, but these actually correspond to the highest altitude locations we have in our cross-validation setup. And so it's kind of a reassuring sign going forward. We're also improving on other Gaussian process benchmarks, where we're just using the high fidelity data and then trying to extrapolate into new locations or into the future. And we're also doing better than state-of-the-art downscaling models that provide the same or similar number of advantages to multi-fidelity Gaussian processes. And so in particular, these are convolutional conditional neural processes and convolutional Gaussian neural processes. And the main reason for this is that are very data intensive. They require tens of thousands of training points to get anywhere close to getting sensible results. So at the moment, yeah, I'm still trying to get these to work, but it doesn't look like for this small amount of data, it would be able to converge on anything sensible. Yes, so now we can apply that model to the whole data set, and here we have some results showing annual and seasonal averages between 2000 and 2010. So the top row here represents the low fidelity data set era 5, and the bottom row is a model's output for both the ES and sublet basins. And here the dark colors represent lower precipitation values, and the lighter colors represent higher precipitation rates. The bottom row we're predicting at a 9-kilometer grid, and this allows for municipal decision making. So, for example, this higher precision could, for example, inform where to place a dam or flood defenses. We, of course, also have the corresponding uncertainty maps that go with these predictions. On the top row here, we're plotting the 95% confidence intervals for the model. Again, the lightest colors represent the higher values of uncertainty and the darker ones, the lower values. I think it's quite interesting to see that here, the highest uncertainties are not necessarily corresponding with the areas where we had no high fidelity measurements, but are mostly centered around the middle of the Sutlej Basin, kind of between the areas that are the foothills of the Himalayas and the areas that are like very high altitude. We can also try to understand the relative uncertainty of the model by highlighting whether the model has a relatively high uncertainty compared to the mean posterior values. And we do this by dividing our data into different quantiles, both the mean posterior values and the uncertainty. And so in the second row, we're showing this, where areas that are light blue have very high uncertainty values compared to the precipitation predictions that are being estimated. And then conversely, the areas that are shown more in pink, even though the model is predicting very high precipitation values, is very confident and has a low uncertainty or smaller uncertainty interval. And this makes sense because these are the locations basically where we had our high fidelity measurements.
Is the uncertainty being clipped if it's predicting no precipitation because it can't go negative? So if you go back and
yes, so to fix that problem, I actually do a data transformation on the data before I feed it to the model, right? So Gaussian processes assume that the posterior distribution is going to be normal, right? So in order to get around this problem, we basically do a transform on the data to make it such that is going into the model looking at Gaussian as possible, and then transform it back when we're making the prediction. So actually, all of the distributions that are output at the end, they look a lot more heavy-tailed than a Gaussian distribution, which is actually corresponds well to what the data should be looking at.
Right.
Like, yeah. Yes. So we can also compare our model to the environmental gold standard, and this is an output or dataset called Aphrodite. And this product is generated by interpolating gauged data with a custom-made lookup table. So on the left, I'm showing the differences between Aphrodite and our model. On average, for the annual average, our model and Aphrodite generally agree with one another, with our model predicting slightly more precipitation and extreme values. And this is actually matching with the literature that compares Aphrodite to gauge measurements. Aphrodite has a slight dry bias, and it also doesn't capture extremes as well as it should. However, we're seeing more significant differences when we start looking at the seasonal averages. So here's an example of the monsoon. And yeah, I'm still trying to understand where these differences are coming from and why they could be generated in this way. So earlier I talked about predicting on a 9-kilometer resolution and how that was useful for making policy decisions. But what we actually care about is not so much the resolution of the model, but the effective resolution of the model. Is the model generating structure at finer scales, or is it up within means? And we can evaluate this by plotting the power density spectrum of the data, which tells us how much structure is being generated at each of the resolutions. So here we have our I guess like the power or structure that's being generated by the model versus the resolution. And what we can see is that for the multi-fidelity Gaussian process, we are generating at least 5 times more structure than era 5 or Aphrodite for the same resolution. So of course, there are many ways we could build on this work. So in this next section, I'm going to talk about the most interesting ones. One of the obvious limitations for using this linear combination of Gaussian processes is that we are not able to capture nonlinear relationships between the different fidelity levels. This problem has been addressed in part by a paper from Pelikaris et al. In 2016. And in this case, they set up a similar observer framework, but then they're using real deep Gaussian processes. In this case, I mean that the output of one Gaussian process at fidelity t is used as the input of the Gaussian process at fidelity t+1. However, the fact that the DPs have this recursive setup and are fit recursively at each level rather than jointly means that they're very likely to overfit. And this is actually what we found when we applied this model to the data. To alleviate this problem, we could also implement another model called multi-fidelity deep Gaussian processes, which were presented by Cottager et al. In 2018, 2019. And this conditions each of the layers of the DGP on data from the previous one or the previous layers rather than doing it recursively just and independently. But that requires variational approximations and using inducing points. So it'd be a lot more work to set up and get running, and a lot more work to basically babysit that the model's converging in the right way. But it could be an interesting path for further work. The second issue that needs to be addressed is the scalability of the model. So I'm sure you know, but Gaussian processes are extremely computationally complex. They scale with n to the power of 3, and the memory to store the covariance matrix scales with n to the power of 2. So this means that it will be hard to scale up the model to larger areas of time periods using exact Gaussian processes. What we can do is use approximations such as structural kernel interpolation to get around this, and this would be like especially useful for the first layer that's gridded, because we can make use of this gridded structure to speed up inference. And then the last point I have here is that although we've seen that it's possible to improve the accuracy of the data sets by combining different ones together to get better predictions, I think this work has still highlighted that more data is needed to make better decisions in this area. But fortunately, we can use the uncertainty estimates of the multi-fidelity Gaussian process to inform placements of future sensors. And we could do this through a multi-objective Bayesian optimization scheme. And this comes from the fact, or rather, we're using the fact that Gaussian processes can be easily updated with new station information without having to retrain the whole model. So unlike a neural network. So you could basically set a hypothetical new station location with data and see how it minimizes the uncertainty for the whole basin, and then choose or like optimize for the ones that reduce the uncertainty globally. Yes, so to conclude, we've seen that it's possible to use multi-fidelity Gaussian processes to combine sparse precipitation gauge data without a less accurate climate model data. We're creating a product that better captures structure, extremes, predicts at arbitrary locations, overcomes grading biases, and works with sparse data, but most importantly, that gives us principled uncertainty estimates. And in the next few weeks, I'll hopefully be releasing a full 30-year data set. So taking one small step towards helping the most vulnerable communities adapt to humanity's greatest challenge. Thank you. Last sentence sounds better than auditory.
Okay, we've time for questions.
Yeah, thank you. That was great. Quick question. You said the power density spectrum infers that your model is predicting more structure.
Yeah.
Do we know if that, is there any way to verify if that structure is actually present, or is it possible that could just be a hallucination? Sort of.
I mean, I guess like structure here is, well, defining a structure is like basically not noise or something that will look close enough. So they're like basically
Is
area
there a way to check that against ground truth?
to guide against ground truth. What would the ground truth be in this case?
just any past kind of measurements or assessments of the same thing, if they're hard.
Yeah, so the two data sets I showed, what I compared against. I think those are the closest to having some kind of benchmark or baseline to compare against. Sorry, not too far. Yeah, so basically we're trying to see if there's something like not just being generated by some kind of stochastic or a random noise generator. And
Is it noise? Because what I could imagine we would see if you had a 1 degree gridded data set and you just regridded it and split each grid into 10 or like 100, and you would get a 0.1 degree. You would immediately see the power spectrum drop off after the 1 degree because you don't have any data, right? But
yeah,
noise will fill in the power spectrum at that point.
right, but well, no, it won't, because then,
So if you convert a 1 degree data set into 0.1 degree data
you
set,
still get structure, it won't be zero.
the power spectrum will drop off after the 1 degree, right? There is just no information that's at a higher resolution than 1 degree in that data set, even if you extrapolate it, right?
Yes, I
If
mean,
you
like,
add random noise to it, you do fill in that lower power spectrum. Because
so
just the higher,
you can see it as like an integral over the different
as a Fourier,
resolution.
right?
Yeah, it's a Fourier transform. But but then like, it would all be weighted on, I guess like the smallest resolution of the grid box you're using. Right?
So if the highest resolution is 1 degree, then the power spectrum will drop off after that because there's no information that's at any higher spatial frequency. If you add noise, the noise, say, white noise is a multi-frequency noise, right? You have noise for all the frequencies, all the way to like high frequencies, perfect white noise, right? So, and so in this spectrum, if you just put a random noise in this plot, it would be white noise, it would be there would be a horizontal line, right? In this class spectrum.
Okay,
So what you're checking against is not comparing it to noise, but comparing it to uniform kind of grid cells, right? Things where you remove the high frequency components. Such as when you have a model which is climate like 30 kilometer, 90 kilometer high at 1 degree climate model. So it's still like this is a useful check, but it's not checking the noise, it's checking against just taking an error file and making it have a value at each like subdivision, like subdividing it into just and copying the values from the one.
Maybe you should ask, what's the natural scale of the area of fire data set? How many degrees is that?
it's 0.25.
0.25. Okay, so I mean, I think fair to answer your question, 0.25. So anything beyond to the right of 0.25 over here is basically suspicious.
Yes, but it's okay, so I they were petted it and regridded, just so that I can make the comparison, because that would be like the most obvious thing to do if you were just looking at era 5. So I did like yeah, a linear interpolation on both era 5 and Aphrodite when doing this, and I wasn't normalize the data so that, you know, we're comparing line to line rather than having one model that had like more variations. For example, era 5 has like more extremes and more I guess like total precipitation for this area than the multi-fidelity GP does or Aphrodite.
Aphrodite is a high resolution one, then what is
No,
it?
Aphrodite is also on
Yeah.
0.25 degrees.
Yeah.
Yeah.
This is just tells you they have the same spatial resolution, right? And it's the thing where what it's doing is spatial averaging, and then like if you have a nearby data set and then you do spatial averaging and then come back, you lost the high frequency data, right? This is what era 5 kind of does. If you had a high resolution thing, you go to low resolution, match high resolution, you lose something, and the power spectrum will drop at that point.
Mm.
And this is what's often, like, that's why people do these plots, is to check if that has happened or not. And I guess this one will tell you that, yeah, the MFGP is the same resolution as 0.5. So are you checking this because the MFGP does output for all of like for a finer grid?
Yeah, but the grid that you choose for the multi-fidelity Gaussian process is arbitrary. You just have to have the x's at, you know, the input resolution that you want, and then it will give you a value.
Yeah.
But then whether that value makes sense,
Yeah, and so okay, so MFGP is filling in some information. But you can't check if it's a noise or not.
I think, that one way to interpret this would be to say that ERA5 beyond 0.25, ERA5 has no information at all.
Yeah,
And then what Kenza has done is to cover the plausible interpolation.
yeah, and that's why the green line is slightly higher.
And then, but the interpolation being done through Gaussian process is a better principled approach of doing the interpolation than the naive regridding. Moreover, it takes into account the high fidelity precipitation data, which ERA5 doesn't have.
Okay.
And also the Aphrodite has it, but Aphrodite did a very good job of using the precipitation data, and she is. So that's why she has better resolution to point, I don't know, 0.1 or something like that. Or 0.5, 0.05. Does that make sense?
yeah, that's the point I was trying to make. I guess like,
But if it was random noise, it would still
Yeah.
look like this.
okay, I think like what would be interesting is just to like have a generation of random noise and then just like put that in and see
Yeah.
what would
Yeah,
happen.
that would be really interesting. Yeah, but thank you. I think that definitely answers some. I think.
Good, any idea?
I have two questions. So first, I think like precipitation is a very interesting application here. Are you aware of any other like interesting scientific questions in environmental domain that people are still using interpolation but has the potential to apply this method like Gaussian process? And my second question is like, do you think because in 4C people use like JEDI data a lot, and during our GTC we also use JEDI, but we found like it has many missing data gaps. But JEDI is also, I mean, the data set is much larger.
Yeah.
Do you think how applicable this method is to JEDI?
Okay, so the first one was, are there any of the applications where interpolation is used? I mean, the whole field of like downscaling is basically trying to do better than interpolation, right? And I wouldn't even say that like Aphrodite is doing just like pure interpolation, because it is modulating the gauge input with this custom lookup table. So by the way, it's really hard for me to compare directly to Aphrodite because the data is embargoed. I can't even get the locations of where the data is being taken from. And the lookup table is also not public. So there's no way of actually comparing the performance of the model. I can only sort of like estimate the absolute differences between the two. And this is a problem with like all of the data in this area is that, you know, we're basically looking at Kashmir. People don't just like give out the data sets freely. There is political conflict and restrictions on how the data can be used. So I think probably with any locations that have like these small data sets or that might like suffer from these sort of political decision-making issues, that could be a good application. I can't really think of any off the top of my head, to be honest.
I think the ocean seems to be right. There's a lot of missing data.
I just heard from some of my friends, they say that in Asian climates, they have a lot of interesting questions, but the basic method they're still using is still like basic interpolation. You Gaussian that would be very.
Yeah, well, I guess it can be used in any sort of application that in which you have some sort of, one high fidelity and one of the data set. So as Castavio said about ocean, you can read ERA5 with Argo flows or like yeah, it kind of needs to do upscaling for
Yeah.
many applications.
So for Jedi, I think the limitation of process is the size, right? And Jedi is not just precipitation at a 2D grid, it's very high resolution, and you're like talking about the full waveforms.
But let's say you even talk about just carbon or.
Yeah, LA.
But I'm curious, like, how big of a data set could this model actually?
Okay,
Yeah.
so not more than 10,000 points, if
Right.
you're using exact GPs. Then you have other options, they're more involved to set up. So the first one is if you have a lot of data where you're oversampling the function, you can use more sparse Gaussian processes, which basically set up sort of points that are then used as the Gaussian process. Again, yeah, more complicated to do, and you kind of need to babysit the model a little. The other one that you could use are Bayesian committee machines, which basically take an ensemble of Gaussian processes and combine them together. And I haven't used those yet, but I'm planning on trying those out for my next project. And those could be a good way of getting around it. So you're basically cutting up your domain area into smaller grids, and then using that. That's like a little bit more flexible than the sparse GPs as well, because you don't have to make this assumption about the oversampling. If you're using time data, you can also basically do like Fourier analysis and then do GPs on the Fourier transform, and then you can also like map out the Gaussian process covariance function as like a PDE and solve that. Yeah, I have some references I can share.
Even that's the kind of points you can have temperature, wind, there's loads of other things also being sampled in. addition to
Yeah,
this, right?
so there's two problems, right? The large data set, so N, but then also the input dimensions. The issue is, so which I didn't touch on at all in this talk, is that for the Gaussian process, you are making decisions from the beginning about what you think the model should look like or what the output should look like. You have to make a decision about what the prior is and what kind of kernel you're going to be using or what mean function you're going to be using. That has a pretty big impact on the mean that your model is going to output, but also the samples and the probability distribution. When you get higher dimensions, it becomes a lot harder to try to make informed decisions about how these variables are going to be relating to each other, which one should be taking precedence, all of these things. So generally, I would say doing anything above 10 dimensions probably gonna be really hard with Gaussian processes. I know obviously there are people that work with images and so on, but then I'm not convinced that they're making very like judicious choices about the mean and covariance functions. They're just taking square exponential functions and using that.
You need to because let's say temperature and precipitation are two different things where you use it in a kernel because temperature should be smooth, you don't go from 0 to 20, whereas precipitation should be sharp, you do go from 0 to 20, right?
Okay, so
And that's a function of the kernel which would fit in.
So I'm not modeling monthly precipitation, so I'm getting around the headache of having the bimodal distribution.
But if you were to do temperature and precipitation as like y is a vector in both of them, you can't just choose a
So then it would be a multi-complex Gaussian process, which
two kernels.
no, you basically have like two GPs working together to do
You can
that.
have a kernel which works for one axis and work differently for different axes, right?
That's true. So it exists, but there's no like there's different ways of combining the two tasks. At the moment, yeah, still no what was the word? Consensus on which of different ways of combining the multi-outputs is the best. So it's still like an area of research. I guess like That's the thing, right? Well, once you start getting into these more like complicated Gaussian process models, they become harder to start setting up and to put in place.
Just one second. Amelia, do you have any questions? Is there anyone online left standing?
No, just me. It was a great presentation. I learned a lot about Gaussian processes. Thank you.
Okay, so let's try. Using so we use and I think something do you recognize